Hello, dear students. Welcome back to the session on Module 4 Design of Clutches and Brakes. So, the clutch part is over. So, in that, brakes that we have started in the previous sessions, say brake is nothing but a mechanical device used to retard or stop the rotation or the motion of a moving or rotating wheel. So here there are two kinds of brakes that we have come across. One is a block brake, another one is band brake. So block brake means a block or a particular another name given for that block as shoe, which is brought in contact with the rotating wheel, so that rotating wheel that retards its motion. So there may be single block or double block brake, what we have discussed. Now let us begin with the band brake. So this is the second kind of the brakes. So here in the band is nothing but a flexible element or flexible belt type element, which is usually or generally made of a steel strip lined with a frictional material, and it wrapped partially over the drum. So suppose if it is a rotating wheel and there is a belt or a band which is mounted on the wheel or the rotating drum, and this is going to wrap or the uh, mounted over the pulley like this, and this particular angle is called as angle of lap or angle of wrap here. So that is what theta. So that may be up to 180 degrees, or even though it is less than 180 degree also. So similar to the concept of belts, so there are tensions which are resulted here in the belt that we have to consider. Say that may be tight side tension T1, or here it is as per our data handbook that is regarded as F1, and T2 is the slack side tension, which is regarded for us here as per the data handbook notation F2. So these things that we have to consider here are the fundamental concepts of the belt drives are also to be taken here related to the forces exerted in the band, as band is partially wounded or mounted on the drum here, as this band is tightened so that the frictional force is exerted between the drum and the band, and that introduce the brake on the wheel or the brake torque on the drum. So again, there are two kinds of the brands here or band brakes. One is simple band brake, another one is differential band brake. So in this session, we will discuss about the simple band brake. So in the particular simple band brake, a band brake which is said to be simple only when end of the band, one end of the band is connected to the or is fixed to the fixed point, which is a fulcrum here, and the other end of the band that is connected on the lever. So this kind of arrangement is called as a simple band brake or arrangement of a simple band brake. So here we can see that one end of the band is connected to the fixed fulcrum point, and the other end is connected to the lever, and it is called as a simple band brake. And in the previous discussion we have come across, if f value is less than or equal to 0, then the brake is said to be a self-locking brake. But here there is no self-locking condition that is attained here, that we will see in the next session or next particular bits. So no self-locking means this value will not be negative nor 0, so that there is no self-locking condition that is satisfied here. And remaining terms such as F is the actuating force, F1 is the tight side force since it is rotating in clockwise direction. So for clockwise direction it is rotating means this side will be the tight side, and this is to be written as with a notation F1. So this is the tight side and this one is the slack side of the band. So this is to be represented here as F2, and A be the distance between the line of action of actuating force and the fulcrum point, and B is the distance between the other end of the band and the fulcrum point. So these are all the notations what we have to follow during this particular study. And also the tangential force that is also to be considered here. So tangential force, that is because of the torque which is transmitted, and that torque is given by tangential force, which is calculated by means of by using the T by R, torque divided by radius of the drum. So by using this relation we can get the value of Ft, and Ft is also given by the another relation, that is the difference between the tensions, tight side tension F1 minus F2, F1 minus F2. So this is another relation with respect to the FT calculation. And also we have another relation, that is tension ratios, what we have derived in the belt tensions or belt chapter. F1 by F2 or T1 by T2 is equal to E raised to mu theta. So this is another important relation. So by using this relation, say what I can substitute here. Suppose if I want the expression for F1 in terms of Ft, in that case, so F1 if I use, so F1 that is equal to what it will be, uh, where is that pen? So this will be F1 equal to E raised to mu theta into F2. Suppose if I replace this F1 from this expression, so I will be getting what here? Say I have to again use, mm, what I have to use again? Again, I will be getting the value F1 Ft equal to, F1 is nothing but E raised to mu theta into F2 now. F1 is replaced by E raised to mu theta into F2. So here in this expression, F2 is common. So that F2 is equal to E raised to mu theta minus 1. E raised to mu theta minus 1. So that F2, if I want, F2 is equal to Ft divided by E raised to mu theta minus 1. So this is what the expression of F2 in terms of only Ft. So the equation what is derived here also. This is what the expression for F2. F2 is given by Ft into bracket 1 by E raised to mu theta minus 1. So this is what the simplification of this particular equation that is obtained here. So in the same manner, if F1 is required, so F2 minus F1 minus F2 equal to Ft, and F1 by F2 equal to E raised to mu theta. So F1 by E raised to mu theta is equal to F2. F2 value is to be substituted that in that equation of Ft equal to F1 minus F2. So F1 minus F1 by E raised to mu theta. So after simplification, you will be getting F1 as this equation. So this is what the conversion of belt tension ratio, that is by using belt tension ratio and tension difference between the tensions. So the equation is obtained in the form of tangential force and E raised to mu theta form. So here, if suppose if the drum is rotating in clockwise direction, and what we want, if suppose if we want the expression for the actuating force F, in that case, similar to that previous concept, we have to take moment about this fulcrum point, so that the moment given by this F1 is 0. So F gives the moment in this direction, so that is F into A minus, so because this F2 gives the moment in opposite direction, so that's why it is with the minus sign, minus F2 into B. So F equal to F2 into B divided by A. Suppose if you know the value of F2, directly here itself you will be getting the answer for the F. Suppose if you don't know F2, so F2 is converted in terms of Ft, so what we have converted earlier, and that is to be substituted here, so that F equal to Ft into B divided by A into 1 divided by E raised to mu theta minus 1. So this is available in data handbook, page number 270, equation number 13.19c. So this is one of the case when the drum is rotating in clockwise direction. Suppose if the drum is rotating in anti-clockwise direction, so what happens? So what there is a change with respect to the tight side and slack sides. So when the drum is rotating in counterclockwise rotation CCW, so here the F1 is shifted to the right hand and F2 is this one. So earlier case, F1 is this one and F2 is this one because of the clockwise rotation. Because of the counterclockwise rotation, this is the pulling side, will have the more tension, therefore this is F1 and this is F2. So again, taking moment about the fulcrum point, and Fa minus F1b is equal to 0. So the same thing what we have derived earlier. So that F is equal to F1 into B divided by A. That is the equation what we get now. So again, F1 is replaced by Ft into e raised to mu theta, Ft into e raised to mu theta divided by e raised to mu theta minus 1. So this is after conversion. How this conversion is carried out? F1 minus F2 is equal to Ft. But what is F1? F2 is to be replaced by F1 divided by e raised to mu theta by using the Bell tension ratio equation. So that take the LCM and the resulting equation is like this. So this is the other kind, or say another form of the rotation of the drum, clockwise and anti-clockwise. So these are the two conditions that we have to see while designing the simple band brake. And after this, the next bit is, say there are some notes that I have written. Suppose if the lever is upside, in that case, because of the rotation, that is clockwise rotation, the tight side will be this side, that is F1 force that is acting on this side of the band, and F2 with the slack side force acting at this side. Again, taking moment about fulcrum point and equating summation of moments to 0. So the equation is resulting like this, so that F is equal to F1 into B divided by A. Again, with respect to the same thing, suppose if the fulcrum point not at the extreme end, that is somewhere here, like this. So this is available in the page number 270 of the data handbook also. There also we can refer it. Suppose if it is rotating in clockwise direction, no doubt this will be the F1, and this will be this side will be the tight slack side, that is F2. And the equation what we get here, the moment given by this side will be 0 now, or this force will be 0 now. So F into A, force multiplied by the perpendicular distance up to fulcrum point, and the other force is this one, so which is giving the opposite direction, so that F1 into B is the another moment. So the equation for F is F1 into B divided by A. So this is another expression for the F calculation. So we have to see what kind of arrangement or fulcrum point, where the particular fulcrum point is located, or how the particular sketch is given. Based upon that, we have to use the equations of the moment by using page number 270 of the data handbook, equation number 13.19a or 19b, like that, or 19c, 19d. So these things that we have to kept in mind. So this is about the calculation of the actuating force. So the next bit that is related to the design procedure. So design procedure that includes different steps. So here the very first step, that is a torque transmitted. As we know that whenever if you want to calculate the tangential force or the actuating force, tangential force is required. So tangential force is required means we require the torque value. If it is given, that is well and good in the problem statement. If it is not given, so use the basic fundamental equation of power. P is equal to 2 pi nt divided by 16 to 1000. So by using this relation, you have to get the value of torque T in Newton meter. So once you get that value in Newton meter, so this meter is to be converted into mm. So then we have to get the value of torque T here. So this is the calculation of torque T. So in the next session, I will take the complete design procedure. Thank you.